Chapter 9, Bases and Relations of Electric Units, Effects of an Electric Current. Three things must coexist in an electric circuit: electromotive force, current, and resistance. The effects of an electric current depend upon the rate of electric quantity which constitutes it. If any two of the above are known, the other can be determined by Ohm's law. Two systems of CGS electric units. There are two systems of electric units of the CGS system. They are termed absolute units. One is the absolute system of electrostatic units. The other is the absolute system of electromagnetic units. The basis of practical units. The absolute electromagnetic units are usually assumed to be the basis of the practical units such as the volt and ampere, although the latter could be derived from the electrostatic units. The basis for measurement and definition of a current. If a current passes through a conductor, it produces various effects. These effects, by their intensity, give a basis for measuring and defining the intensity of the current. One of these effects is the production of a field of force. A magnet pole is acted on by a field of force. It is attracted or repelled by a current. As the effect diminishes rapidly with the distance intervening between current and magnet, the effect is practically limited in extent to a small volume of space. The volume within which the effect is discernible is called a field of force. Theoretically, a field of force may be as large as the universe. Practically, artificial fields of force are small in volume. The field of force of the field magnet of a bipolar dynamo is little more in extent than the volume existing between its pole faces. The intensity of a field of force can be measured by its action on a magnet pole of known strength. A unit magnet pole is one of such strength that it will attract or repel another unit pole at a distance of 1 centimeter with a force of 1 dyne. The absolute CGS electromagnetic unit of current. The absolute CGS unit of current is the following. It is the intensity of a current which, passing through a conductor 1 centimeter long, bent into the arc of a circle of 1 centimeter radius, will attract or repel with a force of 1 dyne a unit magnet pole placed at the center of such circle. The diagram shows an arc of this radius with its center indicated. Calling the force F, we have, for the case described, F equals 1. This is equation 1. Suppose that the current goes through a complete circle of 1 centimeter radius. Its action on a magnet pole at its center will be greater than in the last case in the ratio of the lengths of the conductors. A circle of radius 1 has a length or circumference of 2 pi. The ratio of the arc of the first case to that of the circle of the second case is 1 to 2 pi. Therefore, as these are the lengths of the conductors acting on the magnet pole, and as the intervening distance is the same in both cases, the force acting on the magnet is expressed by F equals 2 pi. This is equation 2. Example. With what force will a unit magnet pole at the center of a circular conductor, the circle into which it is bent being of 1 centimeter radius, be acted on when a unit current passes? Solution. Substituting for pi in equation 2 its value 3.1416, we have for the force F equals 2 pi equals 2 times 3.1416, which equals 6.2832 dynes. Continuing, the variation of force with radius, turns, and current strength. Suppose the wire is bent into a circle of radius r. The length of the conductor is now 2 pi r, and as far as this change of length is concerned, its action on the pole at its center varies directly with that length. But the distance from the pole also increases with r, and since radiant action varies inversely with the square of the distance, we must account for both. So the direct effect from increased conductor length scales with r. The weakening from distance scales with 1 over r squared. Combining these, the force becomes F equals 2 pi r divided by r squared, which simplifies to 2 pi over r. This is equation 3. Example. Assume the radius of a conductor bent into a circle to be 7 centimeters. With what force will a unit current passing through it act upon a unit pole at its center? Solution, substituting the values into equation 3, F equals 2 times 3.1416, which is 6.2832, divided by 7, equals 0.8976 dyne. Now extending this further, suppose the circular conductor is wound around the circle a number of times, say n turns. It then acts with n times the effect of a single loop. Equation 3 now becomes F equals 2 pi n divided by r. That's equation 4. Now, if the current, instead of being unit current, is some current of strength I, the equation becomes F equals 2 pi n I over R. This is equation 5. Solving for I gives I equals Fr over 2 pi n. That is equation 6. Now finally, if the magnet pole has strength M, then the force will be M times greater. This is because the force between the current and the pole depends on both their strengths. It is a product of two effects. So equations 5 and 6 for a magnet pole of strength M become F equals 2 pi n I m over R. That is equation 7. And solving for current I, we get I equals Fr over 2 pi n m. That is equation 8. To answer example, a magnet pole of 5 units strength at the center of a circle of 11 centimeters radius composed of 24 turns of wire is acted on by a force of 377 dynes. What is the intensity of current passing through the wire? Solution. By substituting in formula 8, we obtain I equals 377 times 11 divided by 6.2832 times 24 times 5, which equals 5.5 CGS units. The tangent compass. If in the center of such a coil a very short compass needle is established, a tangent compass is produced. The compass needle is acted on by the horizontal component of the Earth's magnetic field. The circle of the galvanometer is placed in the magnetic meridian approximately north and south. A current passing through the wire tends to deflect the needle into a position at right angles to the plane of the coil. This is at right angles to the position in which the Earth's component tends to keep it. Action of Earth's field. The Earth's field acts upon the needle with the product of the horizontal component of the Earth's magnetism by the strength of the magnet. This product we may call HM, where H represents the horizontal component of the Earth's magnetism, and M is the force of the magnet. Angle of divergence. At a given angle of divergence, theta, from the magnetic meridian, the lever arm of the Earth's action on the magnet, is equal to the product of the magnet's length by the sine of the angle of divergence. This is shown in the diagram. The Earth acts upon both arms of the magnet with virtual lever arms of length AB, and the sum of the two is as if it acted upon the magnet with a single lever arm equal to the length of the magnet multiplied by sine theta. By the same course of reasoning, we find that the coil acts with a lever arm equal to the product of the magnet's length by the cosine of the angle of divergence. Combined action of coil and Earth's field on magnet. Calling the length of the magnet L, we have for the Earth's action HML sine theta. And for the action of the coil, 2 pi ni ml cosine theta. That is 2 pi times n times I times m times L times cosine theta. In any position of equilibrium which the needle assumes, it will be acted on equally by these two opposing forces. They therefore may be made equal to each other. So 2 pi ni ml cosine theta over r equals HML sine theta. This is equation 9. In this expression, m and l cancel out, and by transposition the formula becomes I equals r divided by 2 pi n times h times sine theta over cosine theta, or more simply, I equals rh tangent theta over 2 pi n. That is equation 10. Let me know when you're ready for